All right, let's talk about that tech interview you've got coming up. Feeling that little bit of pressure about the algorithm questions? Yeah, we've all been there. Well, don't sweat it. We're about to do a super fast crash course in Big O notation. And trust me, by the end of this, you're going to walk in ready to nail one of the trickiest questions they can throw at you.
So, let's set the scene. You're in the interview room. You've just finished mapping out some really elegant code on the whiteboard. You're feeling pretty good about yourself. And then, the interviewer looks at your work, turns to you and asks,
Ah, that question. It's the one that can make your stomach drop if you're not ready for it. But hey, that's why we're here. After this quick explainer, you're not just going to know the answer, you'll actually be excited to explain it.
To make this all click, we're going to forget about code completely for a few minutes. Instead, I want you to think about something way simpler: finding a book in a library. Seriously, this one analogy is going to be the key to unlocking this whole concept.
So inside our imaginary library, we're going to try to find a book in 3 totally different ways. Each one of these methods is going to show us a core Big O concept, taking us from incredibly fast to, well, painfully slow.
First up, we've got the absolute dream scenario. O1, which we call constant time. This is the holy grail of efficiency. It basically means your code takes the exact same amount of time to run whether you give it 10 items or 10 million.
Back in our library, this is like having a magical app. You just type in the book title and bam, it instantly tells you aisle 7, shelf 3, 5th book from the left. Think about it. Does it matter if the library is a tiny room or a massive, sprawling building? Nope. The time to get the answer is always instant. It's constant.
Okay, next up is O of n, or linear time. Now this one is probably the most common and, intuitive type of complexity you're gonna run into. That little n just stands for the number of items you have to deal with. In our case, the number of books in the library.
For this scenario, you've got no map, no catalog. You just have to start at the front door and look at every single book one by one. The relationship here is key. If the library doubles its collection of books, your search time is going to double too. It's a straight, predictable line of effort.
Now here's a really crucial point. Big O isn't about the best case, like finding the book right at the entrance. It's not even about the average case. Big O is all about planning for the worst case scenario. Why? Because as engineers, our job is to build things that don't fall apart when they're under stress. We have to plan for the toughest possible situation.
So, what's the worst case in our linear search? It's having the worst luck imaginable. It's when the book you're desperately looking for is the very last book on the very last shelf in the very back of the library. You'd have to look at all n books to finally find it. That's our upper bound.
And now, we get to our final scenario, O(n)², or quadratic time. If you find this in your algorithm, it should set off some alarm bells. This is where performance can get really, really bad, really, really fast, especially as your input grows.
This search method is just bonkers. Imagine this. For every single book you pick up, you then have to go through the entire library all over again and compare it to every other book. It's nuts. If you have 10 books, that's 100 checks. If you have 1,000 books, that's 1,000,000 checks. It just doesn't scale at all. Hearing about this is one thing, but seeing it is another. Let's actually visualize what these complexities look like on a graph. This is where it all really starts to sink in. Just imagine the bottom axis is the number of books in our library, and the side axis is the time it takes to find one. So for O of 1, our magic map, the graph is just a flat, horizontal line. More books? Who cares? The time stays the same. For O of n, our one-by-one search, it's a nice, steady, diagonal line going up. Predictable. But O(n)², that's a whole different story. It starts out low, but then it curves and shoots straight for the sky. That sharp curve is the visual definition of an algorithm that's going to cause problems.
Okay, so that's the theory. But how in the world do you figure this out in a real interview with the clock ticking? Well, it's actually way easier than it looks. You just need to remember 2 super simple rules to cut through the noise.
Rule number 1. Drop the constants. Look, Big O cares about the big picture, the overall trend. If an algorithm takes 2n steps or 5n steps or half of n steps, the growth shape is still a straight line. So we simplify all of them down to just O of n. And rule number 2, keep the fastest growing term. Imagine your code does one thing that's O of n² and another thing that's O of n. That n squared part is going to get so huge, so fast, that the little O of n part basically becomes irrelevant. It's the bottleneck. So we just drop the smaller term and call the whole thing O of n squared. Easy.
All right, let's bring it all home. You get the concepts, you know the library analogy, you've got the simplifying rules. How do you package all of this into the perfect answer that's going to wow your interviewer?
First, let's sidestep a couple of common mistakes. If your function takes two different inputs, say two different lists, you can't just call them both n. You got to be more precise. It's O of n plus m. Also, be specific about what you're measuring. Are you talking about time complexity, how long it takes, or space complexity, how much memory it uses? Just clarifying that shows you really know your stuff.
And here it is. This is the single biggest power move you can make. As soon as you finish writing your code, before they even have a chance to ask, you just confidently state, the time complexity of this solution is O(n), and the space complexity is O(1), and here's why. Doing that, it's a total game changer. It shows you're not just a coder, you're an engineer who thinks about performance from the start.
Because at the end of the day, Big O isn't just some abstract thing you memorize for an interview. It's a real tool that helps you make better decisions and write better code. It's what helps you choose the right approach for the problem at hand. So the next time you're starting a project, ask yourself this. Now that you actually know how to measure efficiency, what's the smartest choice you can make? Thanks for joining me.